All right, so we're talking about the rate of chemical reactions. And we talked about last time about how if I have a progress curve, which tells me the concentration of either a reactant or a product versus time, right? Then the slope of that progress curve at any given moment will give me the rate of reaction at that moment. So if I'm interested in the instantaneous rate, the initial rate, that would be down here. The instantaneous rate at any given point along here would just be a tangent to this line, or to the progress curve, right? And the average, if I wanted the average between a couple of points here, I would just connect those points and find out the slope. Again, because the slope is concentration versus time, y over x, rise over run. So that is your, the slope there is the rate of the reaction. All right, so this is a reaction as reactants are consumed, and we have here an average rate that takes into account this point and that point looks like. Here's an instantaneous rate taking into account there. And again, the slopes are going to be concentration versus time. Here it looks like it's per seconds. All right, the average rate, if I take the average rate from in between 2 points, then I'm going to just take the slope between those 2 points. So what is the most likely average rate of disappearance of B between 10 and 40 seconds?
10 and 40 seconds. So let's see. Y-axis, concentration of B in molarity. X-axis, time, and there's 10. So at 10, it looks like we have about 0.2, is that right?
Okay, maybe a little bit less than 0.2, but we can say 0.2.
And then at 40, you got maybe 0.03.
Okay, so I have 0.03 at 40 seconds. And at 10 seconds, we got about maybe 0.19. Is that okay?
Okay, that's okay.
So at 10 seconds, we got about 0.19. Now, do you remember how to find the slope of 2 points on a line?
No, I don't remember.
Well, it's always change in y over change in x, right? So what is our y-axis here?
The concentration.
Yeah. So if I want to look at the change in y, I can take this 0.19 minus 0.03, or I could take 0.03 minus that one. It doesn't matter which one I subtract from the other one in that order, as long as I use the same over here, okay? So let's do 0.19 minus 0.03, because that'll give us a positive number. So that's 0.16, right? So that's 0.19 minus 0.3. And then 10 seconds minus 40 has to go underneath it. So that's a negative 30 seconds. So if I take my 0.16 divided by negative 30, I've got a slope of 0.0053. Let's see, did I do that right?
Well, it looks like it's probably supposed to be around 0.006.
Yeah, it probably is. You know, we kind of estimated these points, and we might be off a little bit. So, is it negative or positive?
Oh, it's the rate of, I don't know. What do you think?
Well, that's kind of a, question that shouldn't be asked at this point. We haven't really talked about it. But because it's saying the rate of disappearance, how fast does it disappear? Well, this is how fast it disappears. If it was the rate of change, then it would be the negative value. But again, this isn't, we're not going to be that specific about things. The thing that you want to recognize, you would know that this has a negative slope, and that negative slope means that the concentration of material is disappearing over time, right? So, good job. All right. Now, we mentioned already that the rate of the disappearance of one reactant versus time corresponds to the rate of the other reactant's disappearance over time, according to the stoichiometry. So if I were to put a 2 in here, that would mean that for every reaction that occurs, 2 A's disappear and 1 B disappears. So the rate at which A would disappear would be twice as fast as the rate at which B would disappear. I think I said that right. The rate at which A would disappear would be twice as fast as the rate of B would disappear. All right. Let's put in the stoichiometry here a 3. All right. So the rate of appearance of C, how would that relate to the rate of disappearance of B?
C would appear 3 times faster than B disappears.
That's right. That's right. So, again, you can make statements about the rate of disappearance of different reactants or the rate of appearance of different products based on their relative stoichiometry. Okay? So, here's an example. Here's a chemical reaction, and we measure the disappearance of substance A to be 3.5 times 10 to the 5th. What does this stand for?
That's molar per second.
That's right, concentration per second. And so then the question is, what's the rate of appearance of D?
Appearance of D?
Yeah.
Let's see, 3.5 times 10 to the minus 5 is for which one?
It's for A.
Okay, so 5 times faster?
Well, not quite 5 times faster, right? Because there's a 2 here.
Oh, yeah. So you have to divide by 2 and then times by 5?
That's right. So if A disappears at this rate, then D is going to appear 5 times faster divided by that 2. So you could kind of think of it as we want to know D's molar per second, right? No negative 1 there. It's already there, down below. D's molar per second. And if we start off with A's molar per second, and that value is 3.5 times 10 to the minus 5, right? Well, we can use as a conversion factor 2 molars per second of A is going to disappear at the same rate of 5 molar per second of, this is A and this is D. All right, so it's going to be 3.5 times 10 to the minus 5 times 5 divided by 2. Okay, in the reaction 3A, 2B, and goes to 1C, we measured the rate of B. How does the rate of C relate to the rate at which B disappears?
C will appear at half the rate at which B disappears.
Okay, very good. So every 2 B's that disappear, you get 1 C. So the rate of appearance of C will be half the rate of the disappearance of B. Okay, very good. Here's another one. The rate of the reaction of carbon monoxide is measured to be 2 molar per second. What would the rate of the reaction of, what would be the rate of the reaction of oxygen gas?
Well, 2 molar per second, and oxygen gas, carbon monoxide has a 2, oxygen gas has 1. So it'd just be half as large, right?
That's right. It would be half as large because the stoichiometry here is 1 and the stoichiometry here is 2. All right. Does that make sense?
Yeah, I get that.
Excellent. All right. So that is a good place to stop. We'll see you next time, all right?
Okay.